Um, okay, so today is pretty much the last day that we're going to learn. There'll be a few reactions sprinkled in after the exam, but for the most part, in terms of like a lot of reactions thrown at you guys, today is really the last group of reactions. It's really only a single reaction, but as we'll see, it's really a new class of mechanisms, and from that mechanisms, there's going to be a variety of different transformations that we can do, and it involves metathesis, a reaction. Specifically, alkene. Okay. And as you guys know, as you guys should know, if you were to take a molecule such as, all right, let's just say, for example, CH2, here, CH2, let's get hydrogens out of the way. What a metathesis reaction is it's a reorganization of alkenes through a process that, as you guys would guess, is not a thermally allowed process, right? And that's going to be a first step of 2 plus 2 to make. Now, this is not the real mechanism, as we'll see. Sort of get to what the real mechanism is in a second. We know that this 2 plus 2, right, is not a thermally allowed process. You can do this photolytically for the reasons that we stated earlier when we were talking about cycle additions. But we're just going to use this as a sort of method to understand how metathesis works. And then what will happen is you can actually do another, what will lead to ultimately the bond rearrangement, that's why we call it metathesis, is it will actually get to sort of a rearrangement of alkene carbons. Right? And so as you notice that through this sort of 2 plus 2, sort of called retro 2 plus 2, what's happened, right, is that we have, in essence, the alkenes have swapped their partners, right? So these 2 carbons were joined by a double bond. These 2 carbons were joined by a double bond. And through the process of this 2 plus 2, retro 2 plus 2 process, right, we've effectively changed the partners, right? So now, instead of the 2 greens being together, now we've flip-flopped it so that the green and the red are together. Okay? So this is formally how we can think about metathesis chemistry, right? Sort of a reorganization of pi bonds where 2 double bonds sort of can react with one another to ultimately form 2 new double bonds. But we know that this is not a reaction that can take place thermally, right? 2 plus 2 does not work. However, it turns out that you can actually affect this reaction with metals. So again, this is part of the sort of the metal catalyzed carbon-carbon bond forming process. So obviously we can't do that. But what we can do is we can treat this molecule to a metal carbene. Okay? And the metal that we are primarily going to be using is ruthenium. We can discuss the entirety of the catalyst. But from the mechanistic standpoint, this sort of ruthenium alkylidene is the important point. The catalyst is a little bit more complex than this, but for the sake of looking at the mechanism, we'll oftentimes just abbreviate the metathesis catalyst as the ruthenium with the double bond. These are the overwhelming majority of catalysts that are used to date for metathesis and employ ruthenium. There's some differences between them, but for our case, we'll just keep it that, okay? And it turns out that because ruthenium is not beholden to those same sort of molecular orbital theory that we sort of discussed previously in terms of, conjugated pi bonds or alkenes that are based upon s and p orbitals. Obviously, now we're able to go into d orbitals and so forth. So the hybridization, the molecular orbitals are just different, right? And so these can do 2+2 reactions, okay? And what happens, I'll just sort of draw this on its side. What happens in a ruthenium cathexis reaction is that now we can do a 2+2. Okay, so this can happen. Okay, and then when we do the retro 2+2, watch what ends up happening, right? For the sake of what we're doing, it doesn't really change anything, but it'll become clear. It's part of why we have the colors here. Oh, you know what? To stay consistent with what we did previously, I'll show the electrons. Doesn't matter which way we go, we're going to get to the same thing, but just to sort of stay consistent with what I was doing before, I'll just do this, just to keep things simple. And again, we're sort of focused on ethylene at this point. It'll become a little more clear when we start getting to actual exact examples, right? But just pay attention to the fact that what we have done is we've taken ruthenium alkylidine, right? And through this 2+2, retro 2+2, we have generated a new, right, ruthenium double bond, which is now double bonded to the alkene that we started with, right? So we'll get into some specific examples why this is important later on, and it's more productive, but right now we're just going through the mechanism to show how we can get to there. Right now, this new ruthenium alkylidine can do what? It can react with now that can react with the new alkylidine, right? Right, to get to our metallocyclobutane, right? And then, what's going to happen? Right, is we can effectively promote the sort of bond reorganization that we did previously, right? So the general idea here, right, from the metathesis is we can imagine it in just a couple steps in terms of just visually thinking about it, right, at sort of a 2+2 followed by retro 2+2. But as we sort of discussed, that can't happen, right, because thermally you can't do that 2+2. However, when you bring in a ruthenium alkylidine, right, that can promote the 2+2 retro 2+2. Through that process, we generate a new ruthenium alkylidine, which, again, then following the 2+2 retro 2+2 can affect that sort of crossover. Yeah?
Yeah, so how do we know when does ruthenium stop reacting?
So we'll discuss actual examples, but Faraj just brought up a point. How do we know when the ruthenium stops reacting? And we'll show some specific examples. This was just with ethylene to show the general mechanism. But Faraj rightfully points out that we're regenerating a new ruthenium alkylidine. And so we'll see this is in fact a catalytic process, and what we will discuss is what are some of the things that can drive a metathesis reaction. Okay. All right, so some of the first metathesis chemistry that was developed was actually for polymerization, which we're not going to discuss today. We can discuss ruthenium polymerization once we get to polymer chemistry in a few weeks. What I want to focus more is on small molecule synthesis and discussing how this could work. So everybody should have a piece of paper and pencil out, because the mechanism of metathesis is fairly straightforward, right? It's just 2 plus 2, retro 2 plus 2, 2 plus 2, retro 2 plus 2. So even if you've failed miserably at all these other mechanisms and you just struggle with mechanisms, this is potentially a chance to get back, because ruthenium metathesis mechanisms are pretty straightforward. 2 plus 2, retro 2 plus 2. And they aren't necessarily beholden to a lot of the other mechanisms. And you will likely get a mechanism question on metathesis at some point. So this is a place where you can really hopefully you can even if you've struggled with mechanisms, you can hopefully get this one. Okay? All right, so there's a few different types. Like I said, the earliest metathesis was polymerization. We won't discuss that today. What we're going to focus on is really 3 classes. We're going to focus on ring closing, we're going to focus on ring opening, and we're going to focus on cross metathesis. Okay? So let's discuss ring closing metathesis. Okay, so here's a 1, 2, 3, 4, 5, 6, 7, 7 carbon diene. And what I'd like us to do as a class is, based upon what we discussed earlier in terms of the mechanism, what I'd like to do is try and have you guys think through what the product of this ring closing metathesis is going to be. Okay? So what is the first step of this reaction based upon what we've seen? It's going to be the first step. Yeah, Faraj.
Ruthenium catalyzes the first 2 plus 2 reaction.
So we've got our ruthenium alkylidine. We've got our alkene. Doesn't matter which one we pick. It turns out that we can actually do the ruthenium 2 plus 2, retro 2 plus 2 in a few different ways, and I'll just sort of make that clear right now. Again, everything is reversible. One way that we can do this would be like this. All right, I'll just say, we'll just clean it up. So, for the sake of color, maybe we'll make this ruthenium. Let's make the ruthenium green. Right, if we do that 2 plus 2, right, we're going to end up with I'm just sort of leaving out the carbons at this point. Just go back to line angle notation for the time being, right? And I'll just put an R group here for everything else that's left over there. But what's going to happen is, if we go this pathway, we can go the 2 plus 2 this way. Right? Where's that going to lead us? Back to the starting material. We can go that way. Where's that going to lead us? Effectively back to the starting material. It's going to lead to a bond reorganization. We'll get the green now incorporated into the alkene, but it's not productive, right? We're just doing bond reorganization. And that's fine, right? The metathesis reaction can do that, and you might get some scrambling. For example, if this was, say, for example, C18 labeled, and you start doing some of this chemistry, maybe you might get some scrambling that would be important from that, but I wanted to show this route just to sort of recognize that, you know, there's nothing wrong with this, but it's just non-productive. The productive pathway would be as if we flip-flop it. So if the ruthenium's on this side, and the alkylidines on this side. Right, so I'll draw it below. So this will be our green arrow. Right? If we do it here, use red for this one. Right? Now we can do our retro 2 plus 2. Again, if we go this way, what's going to happen? We're going to go back to the starting material. However, if we just switch them over one, what's going to happen? Now we're going to get a new molecule. I'm just going to switch back to the ruthenium at this point. I'm just going to make it all white at this point. But now our ruthenium is actually going to be on the alkene chain, right? And that's going to be productive 1, 2, 3, 4, 5, right? So that's going to be perhaps the productive pathway, right? You know, the first step is oftentimes getting the ruthenium alkylidine onto something, right? Now that we've got it on the one alkene, what do you guys think? I said this is going to be for a ring-closing metathesis. What do you think is going to be the next step? It's going to be an intramolecular 2 plus 2 retro 2 plus 2. Is it easy to see as we have it drawn here? No, so we probably might want to redraw it, right? And if we want to number our carbons, this is sometimes where numbering our carbons can be helpful. 1, 2, 3, 4, 5, 6. Okay? And we know, right, that ruthenium, right, that what we want, right, is we want that ruthenium reacting with that alkene, right? And so if the ruthenium is 1, if this is 6, 5, right, then what do we have? 2, 3, 4, right? So what we're going to have here is 2, 3, 4, 5. Okay? And now that we've redrawn it, it's probably going to be a lot easier to see the reaction. So what's going to happen? We're going to do our 2 plus 2. Right? Generate the ruthenium metalocyclobutane, right? Final step. Right? Is going to be cyclopentene. You see that? In the process, we're going to regenerate the ruthenium, right? So we could certainly draw a catalytic cycle that shows this as well. Maybe we can do that as well. But the net result, right, is that we're going to regenerate the ruthenium alkylidine, so the ruthenium alkylidine can re-enter the system. So this is a catalytic process. You know, you just need a little bit of the ruthenium alkylidine, and you can do the chemistry over and over and over and over and over and over and over again. Okay? Make sense? All right, so back to Farage's sort of question earlier. Ring closing metathesis is actually one of the easier reactions to have been developed. Aside from the original polymerization chemistry, ring closing metathesis was the first sort of controlled small molecule reaction. Farage, why do you think this might be a productive reaction?
Because we're going from a chain to a ring.
So we were going from a chain to a ring is not necessarily, that's a circular argument. Right? That's just making an observation that it was a long chain. Do we know that rings are better than long chains?
Possibly.
Well, what do we know, Irina?
I mean, I think it's unique that it can create a situation of strain that it's willing to go through. And
Well, 5-member rings aren't really strained. 5-member rings are so.
you go through the form.
Oh, yeah. Well, remember, it's the ruthenium. I'm drawing it as it's the ruthenium. The bond is much longer, and so it's not the tight squareness, excuse me, that I necessarily drew there. Yeah.
Got rid of the double bond. And do you have a more substitute double bond also?
Yeah. So that's one of them. We've got a more substituted double bond. So energetically, we've seen that can be favorable. So that's one thing that we might look to this and say, hey, ring closing metathesis, we're generating a more stable, if we're assuming this entire process is reversible, right, going from monosubstituted alkenes to a disubstituted alkene, yeah, that would jive with what we've discussed in terms of energetically favorable processes, right? That's one thing. What else? There's one other thing that happens here, right? If we look at the overall reaction. So thermodynamics can certainly drive this by sort of more substituted double bond. Something else. What else do you guys think? Well, I'll give Raquel a chance unless somebody else got some thoughts. What else? How else do we drive reactions? How else have we driven reversible reactions in the past? Well, heat just will lead to equilibration. How do we drive them in one direction oftentimes? We saw this, yeah. So yeah, in the case of the water, what did we do? So in the dehydration versus hydration reactions, how did we drive those? Well, but was physically what drove a reaction? Because oftentimes hydration and dehydrations were simply the opposite reactions, right? And if you wanted to do a hydration, how did you push it? Yeah.
We use the Chavalier's principle.
Yeah.
Excess of one.
Right. Exactly. So you could either drive it in one direction with water, or conversely, we could eliminate water. Right? Aisha, so what do you think about this? You had your hand up earlier, but now I'm going to let you answer this. So Le Chatelier's principle, right? So we would drive it by Chatelier's principle. Well, let's look at our reaction here. Do we see anywhere, maybe we're missing things in this reaction? Maybe there's something that I haven't drawn that might help us. I've drawn it, but I haven't actually physically drawn. Okay, so I did our 2 + 2. That's all conserved. Have I conservation of mass, conservation of energy? What am I missing here? The alkene, right? That's something that I didn't show here. What is that? Ethylene. What do you guys think about ethylene? It's got 2 carbons, 4 hydrogens. What do you think? Physical properties of a molecule like that. Completely nonpolar, very small. What other things have we seen that have similar weights to ethylene? Nitrogen, oxygen. Guess you aren't going here. What do you think ethylene is physically? At room temperature. Yeah. It's a gas. So what do you think happens when the ethylene is generated here? Leave the system. Right? So through Le Chatelier's principle, so thermodynamically, this process could be driven, right? Perhaps by generating a more substituted double bond. The process could also be driven because we're generating a gas. And a lot of times when we generate a gas, that gas leaves the system, right? And with it no longer being in the system, via Le Chatelier's principle, it can't go, we're basically rendering it no longer reversible, right? Right? So every time that ruthenium enters the system, we're extruding the ethylene gas. Overall, this process is generating, if you think about the overall process, it's generating every time it does this reaction, it's generating this, and it's generating acetylene. You push it in this direction because that acetylene is a gas and it's going away. Okay, does that make sense? Okay. So this is ring closing metathesis. Actually, I lied earlier when I said there's only 3 classes. There'll be a few others, but really 3 classes. All right. So this is ring closing metathesis. All right. So let's we can do ring closing metathesis. We can potentially do ring opening metathesis. Okay? Just for this is going to make this 6-membered. I'm just showing this as an example. You know, I showed it earlier as a 5-membered. I just happened to draw that as a 6-membered. So obviously we can make different size rings. We can make 7 members. We can make 8 members. But that's ring closing. This is driven by ethylene. More substituted double bond. Perhaps there's some stability in the ring system, for example. I don't know that there would be, but that's sort of ring closing. So everything seems to be pointing in the direction that this reaction would favor ring closing process, right? If we were going to try to do a ring opening, right, that might be a little bit more challenging, right? If you were going to try to go in the reverse and go from a 6-membered ring to a ring open version of a 6-membered ring, that's going to be a lot more challenging. And in fact, people rarely do. I'm trying to think, it's been a while since I read about the state of the art with metathesis. But I think that people have done it. And I remember when I was looking at reading a lot more about this reaction at the time, people have been able to maybe get like 1 turnover with this reaction. It's very difficult to go in the reverse direction. But that's partly because this is more stable, right? Where you can do ring opening is perhaps when that cyclic system is not that stable, in which case you might not want it. So Irina's, what's that? Like maybe a 4-membered ring, right? So maybe ring opening, and this is usually when people talk about ring opening, strained system. So a 5-membered ring is not that strained, but a 4-membered ring is strained, or maybe a 3-membered, right? So if you have a really strained alkene, right, and you treated this with the ruthenium alkylidine and say, for example, ethylene gas, would be the product. So what I want you guys to do, I'm going to give you guys 3 or 4 minutes. I want you to go through the mechanism of this and predict what the product of this would be. I'd like you to predict what the product of this would be. Okay, so let me give you guys a few minutes to reflect on the metathesis reaction and try to figure out what the product of a ring opening metathesis would be of both of those. So what's the product of this one? Spend a little bit of time unless you have a different question. Okay. So everybody give that a shot so we can practice the metathesis mechanism and try to predict what the product is. All right.
Sorry, we always want to get rid of the ruthenium at the end.
Well, it regenerates the alkylity. All right. So let's go through it together. So Faraj, what should we do first? What should be the first step?
The first step, the ruthenium aligns.
I'm going to start with this one just because I drew it here.
Right. So the ruthenium aligns with that bond.
Mhm.
It makes the square. Right.
The metallocyclobutane. Yep, that's going to be the first step.
Those electrons also get pushed the same direction, and then you get the ruthenium on the outside of that mixing ion. And now with
Yep.
the
Now we've got to regenerate our alkylidine. So what are we going to do?
So with the ethylene gas that we're putting in this
Mhm.
system, it aligns with the ruthenium,
Mhm.
and then it forms the ruthenium butane. And then the arrows get pushed the same way, and then you get two double bonds on the end of the chain.
Yeah. So and then we regenerate our ruthenium, right? And the ruthenium keeps going. Ronnie.
What kind of stereochemistry would we have to use?
So we haven't discussed cross metathesis yet, so there is no stereochemistry to the alkenes that we've seen yet. For six-member rings, for ring-forming reactions, usually what we're going to do is make cis, right? Because trans six-member rings, trans five-member rings aren't going to happen. I'm trying to think of what happens on macrocycles. I'm trying to think if maybe trans might happen on big cycles, but let's not worry about that right now. Okay. All right, does this make sense? And so this is 1, 2, 3, 4, 5, 6. So it's a sort of a hexadiene, right? 3-member ring. If you didn't figure it out yet, the 3-member ring would be the same thing, just one less carbon, right? So it would be basically the pentene, right? The linear pentadiene. Okay. All right, so this makes sense? It's pretty straightforward. Mechanism is a little bit different than what we've seen in the past, but it's pretty straightforward, right? You do the 2 plus 2, you do the retro 2 plus 2, keep pushing the arrows in the same direction, you get these bond reorganizations. Okay. All right, so ring closing, ring opening. In both cases, stereochemistry really isn't relevant because we haven't shown any stereochemistry. But what we can do, and where stereochemistry can come into play, will be with cross metathesis. Okay? Okay? And a cross metathesis is, we just discussed cross coupling previously in terms of taking an alkyl halide and some type of alkyl metal, and we cross them, we bring them together. Cross metathesis is a process where we actually take 2 alkenes, right, and we actually can make the disubstitute double bonds. Now, Ronnie was asking about the stereochemistry of the EZ double bond geometry. That's a little bit more complex of an answer in actuality. It's going to depend largely upon the nature. It turns out that the kinetic cross-metathesis product, at least classically, is the cis. But what ends up happening is, because it's a reversible reaction, it'll eventually make the trans. So you can often render metathesis trans-selective by taking advantage of the thermodynamic control. For the sake of this class, let's just simplify it and just assume that these are generally going to be reversible and so that they'll lead to trans. So let's just simplify it and say trans, double bonds, thermodynamic control, easier to do. All right, why don't you guys spend a couple minutes trying to reason a mechanism across metathesis. Just give you guys a couple minutes, try that on your own, try to do a mechanism that can show the cross metathesis.
In synthesis, will we have to generate the ruthenium or?
No. No, yeah. No. We'll regenerate the ruthenium.
Oh.
Yeah, you should always assume that the ruthenium comes off at the end. Unless, I can't think of a specific question that would do it. But again, it's catalytic, so it's like the last step is always regenerating the ruthenium. All right, well, at this point, we should all be able to do the first part of this reaction, right? So let's just start with the left-hand ruthenium, right? And again, depending upon how that ruthenium aligns with the double bond, again, it can align either way, but the productive way is going to be the one where the ruthenium ends up being incorporated with that R1, right? So the question that people would have is, well, why doesn't the ruthenium go the other way? Well, it could go that other way, it's just not going to be productive, right? So eventually it will align itself in this direction. We'll do our 2 plus 2. And then we'll do our retro 2 plus 2. And now we've got our ruthenium double bonded to an alkene. You know, we've got our ruthenium double bonded to a carbon, where that carbon now has sort of information of the R1. Right? Now the challenge, or the potential thing here, right, is this goes back to how does the alkene perhaps line up? Right? We could line up the alkene this way. Right. So if we line it up that way,
It does get a cis.
right, we're just gonna flip-flop which one has which. The ruthenium will end up then having a double bond to this carbon, and on that carbon you can go through that on your own, but you can clearly see that what we want is to make a double bond, so we want that R2 on this side in order for us to get there. Make sense? So again, it's all reversible. It's not why can't I go in this direction, because all these steps are ultimately reversible. It's just that it's not going to be productive going that way.
This gives us a cis product though.
Yeah, that's what I'm girls.
What do you mean? We didn't show any stereochemistry. There's no stereochemistry.
There is that's
No, the stereochemistry is going to be based upon whether this R group.
right, so it's cis over here.
Well, so you have a proton here, right? No, because I didn't show stereochemistry. What if I had that? Yeah, you're just looking at it. You're oversimplifying looking at it because we hadn't shown stereochemistry there.
But I mean, according to this drawing, you still do have a cis. I mean, it will become a cis alkene.
No. Well, it depends upon because you can't. There is no stereochemistry as is drawn there. I haven't defined the stereochemistry there.
Once you make the double bond, there will be.
No, because I haven't decided. You don't know what the stereochemistry is. Because I haven't defined what the stereochemistry here or here is. You know what I'm saying?
Maybe I'll get it if we go through.
Right. Well, no. So there's a proton here and here. So if these groups are on opposite sides of one another, if this is coming.
Okay, so okay, I understand.
See what I'm saying?
Yeah.
So it depends upon what the stereochemistry is here. If they're cis to one another, if R2 is here and the proton is there, then you would get cis. And like I said, you know, the classic, different catalysts will do different things, but classically the cis is the kinetic product, but again, just the reversible nature of that leads to trans. I think for the sake of this class, let's just assume it goes trans for the cross. We can reason that by saying that this is a reversible reaction and it will lead to the thermodynamic product. Faraj, you had a question?
Yeah, I was going to say the step immediately before it, that carbon that we're talking about is trigonal coherence. So how do I know if that proton is coming in or out of the board in the
You don't.
step after it?
You know, that's what I'm saying. We haven't really discussed how this cycle addition would, you know, it's going to basically be based upon whether it's flipped over and how the alignment is with these different, you know what I mean? It's good. Don't worry about that. Don't worry about that. Okay? We regenerate our ruthenium alkylidine, we generate our trans double bond. Now, what do you guys think, aside from the stereochemistry, what are some of the potential challenges with a cross metathesis? What do you imagine might be some of the problems and challenges with the cross metathesis?
You get a lot of byproducts.
You get a lot of byproducts. What would those byproducts be?
You can, I mean, if you want to get the cis, you get the trans.
Okay, so cis and trans stereochemistry could be one problem.
Also,
But let's assume that that we can render this reversible and get to the thermodynamic product.
well, R1 can bond with R1.
Yes, that's kind of what I was getting to, right? Is that R1, right? You could also get, so this is a sort of you know, the cross, but we could also have the sort of the dimerization, if you will, of this one, or the dimerization of this one as well, right? And this is one of the challenges with cross metathesis. You know, if you wanted, usually, how might you, in practice, you know, how might you sort of force getting that product? And this is maybe I'm asking you guys to read my mind here a little bit. But let's say, for example, that my R1, let me just put a scenario out there for you guys. Let's assume that R1 is really precious. It took me 20 steps to synthesize a molecule that was that. What might I want to do in that case? Yeah.
You want to have it in two different reaction processes. You want to have two different steps. First, you want to create the ring.
It's an alkylidine, so it's catalytic, right? So you're not going to use stoichiometric ruthenium alkylidine. Oh, that's a good idea. That would be something you could do if we could get away with stoichiometric alkylidine, right? Irina?
And like excess?
Yeah. So which one do I use in excess of? If this is precious, I'd use an excess of this, right? So that's one of the ways that people can force it in one direction. It also turns out that there's some electronic differences. Yeah, Mark. Right. So if we made this our linear reagent, we use this in excess, we'd have a whole bunch of the dimer there. Well, because we would have gotten a high yield based upon what we care about the most. That was the scenario, was if this was precious. Right? So we'll sacrifice, and yes, we'll still have a lot of byproducts, but they won't impact our yield of this. If this is really precious and we tried going 1-to-1, then we'd have some dimer of this. We're trying to prevent the dimer of that, right? Because that's going to be non-productive from the yield standpoint. Yeah, right.
Excess of R2 would make a dimer of R2.
Absolutely.
And
That's
then-
kind of what Mark is saying, is you still have a lot of the R2. Absolutely.
I'm saying that form like double bond between three different groups, like R2, and R1.
No, you can't. No. You can't get to. No, you can't. No, the alkene's not going. You're not going to be able to do You can't do metathesis this way, at least, to get sort of tri-substituted alkenes. Right? It's not. You're not going to be able to do that. So, but again, the other point is that it turns out that, and again, we're not going to go through this that much, but it turns out that like if you have electron-poor alkenes with electron-rich alkenes, for example, there is some electronic benefits to the metathesis that people have figured out where sometimes you don't necessarily need to use a large excess of one. Sometimes they're matched well. And that just has to do with the sluggish nature of how the ruthenium gets on one and then the relative reactivity. It gets a little bit complicated beyond the scope of this course. All right, so metathesis, ring closing, ring opening, cross. These are the ones that that are the sort of the classic ones. Let me throw you guys a little curveball here. All right, so this is alkene metathesis. If you look through the book, right? I'm thinking back to last class when we discussed Heck chemistry. And some of you guys did some of the problems in the back of the book with Heck. So Heck is chemistry on alkenes, right? Faraj is nodding his head because maybe he knows where I'm going. What do a lot of the books have? They throw in something instead of an alkene. Throw in an alkyne, right? So a lot of times what the book will do is they'll have these mechanism questions where instead of an alkene, it'll have an alkyne. But if you go through the mechanism, you should be able to get there. So this brings up another type of metathesis, which is called enine metathesis. Enine metathesis. And let's do a little thought experiment. What might happen? Let's talk about it. Let's try to go through it. Let's try to reason it. Here's a ring closing enine metathesis. Let's spend a little bit of time. It's a little bit more challenging. I'll give you guys a little bit extra time on this one. Let's try to predict what might happen if instead of an alkene, a cyclic system where we had two alkenes, let's try to predict, based upon our knowledge of the mechanism, what might happen if the ruthenium were to react with this molecule. Now, there are a couple different mechanisms and a couple different products that you can draw, one of which actually happens. I don't care which one you get. I just want you to go through the process and try to come up with something. Okay? And the net result has to be, though, that you're going to liberate the ruthenium alkylidine. Okay, so spend a little bit of time on this. We got some time. Just try one or the other. Yeah, we can discuss which one it would go after first. This is a debate that's been had. This is a debate that's been had on people that have spent a lot more time thinking about metathesis than you have currently. So just try one. Just pick one and go with it.
Well, we know it can go to the double bond.
At some point, you're going to have to go to the triple bond. The question becomes: do you want to go to the triple bond first, or do you want to go to the double bond first? And what I'm saying is that try them both. See what happens. Or just try one for starters and see what you come up with. Anybody got anything? Just a little more time. You're not going to do really triple bond.
Wasn't never at this.
No. You don't get to a ruthenium triple bond. You got to a ruthenium triple bond, you're not going to get to a ruthenium triple bond. Can you guess on that? Sorry, yes. Sounds like with your hand. Probably have it. Double check your carbon. And you're fluctuating that between having not enough and having too many, and you adjust that, or just make sure that your carbon count's right. All right, so you guys have a little bit of time on this. All right, so as I sort of stated, we can look at both ways, and we can try both ways for starters, and we can see that depending upon the way that you go, you may be able to get multiple products. It turns out that the way that I'm about to show it to you now is the way that it actually does go. The ruthenium is first going to react with the alkene. Okay, so we're going to have the ruthenium alkylidine react with the alkene. That's okay if you showed it with the alkyne, that's fine. We'll go through that mechanism as well. But if this were to react, right, what's going to happen is we're going to be, I'm going to swing it over. Let's count our carbons, right, from our ruthenium. It's going to be 1, 2, 3, 4, 5, 6 to the alkyne. 1, 2, 3, 4, 5, 6. Again, just make sure a lot of times when we start drawing these more complicated molecules, we really got to pay attention to make sure that we haven't added or subtracted any alkenes, or sorry, carbons at that point. All right, so that's going to be the first step. And now what we have to do right now is where it gets a little bit different than what we've seen in the past, because now our ruthenium double bond carbon is now going to react with the alkyne, right? The other pi system that it has, right, is the alkyne. Okay? 1, 2, 3, 4, 5, 6. It's going to be a 6-numbered ring. Okay? All right, we're going to get to, and in this process, what did we lose? We lost ethylene gas, which we'll have re-enter a little bit later on. Okay? Now what can happen? Just keep pushing the electrons this way. See that? Just pay attention to the electrons, pay attention to your carbons. You should be able to see this, right? Instead of it being a metallocyclobutane, right? This triple bond, instead of usually it goes from a double bond to a single bond, now the triple bond is going to a double bond. Triple bond is going to a double bond. No different, right? The difference now, though, is that when we continue to do our sort of retro 2 plus 2, if you will, right, we've maintained that bond, right? So generally that bond, right, that bond that was right there, when it was a regular metathesis, right, that was gone. So this is where we would generally regenerate the alkylidene, right? But because we had the triple bond, now we have an extra bond there. Okay, we got to regenerate our alkylidene. How are we going to do it? Ethylene. Right.
Didn't it already leave as a gas?
Yeah, that's what I was saying.
It's already left as a gas. Then why?
Pump in ethylene. We'll keep it in a sealed vessel. So you basically, an enine metathesis, instead of making a double bond, an enine metathesis, you actually make a diene, 1,3-diene. Adenine and then.
Go through the alkyne first.
Yeah, we'll go through the alkyne. We'll go through that next.
You get to the same product without.
You can. There's a couple different products you can get to. So we'll go through the alkyne next.
One question. Once you have the ruthenium on the ring, can it react with like the double bond with other?
Once it's already in the ring,
Yeah, like the step fast.
this.
Yeah, if that ruthenium react with like the alkene or other different molecules.
Yeah, so usually, what time are we looking at right now? Okay, usually when you're doing ring closing metathesis, you usually run it oftentimes under dilute conditions to prevent that from happening. Right, so once the ruthenium's on there, it's much more likely going to see an alkene nearby in an intramolecular case, right, than it is to see another molecule in the solution. So it's oftentimes the case that these reactions are run under dilute conditions to keep that from happening. But you're right, that could be a possibility. All right. Must be 10:30. Voices out in the hallway. George, can you just pop your head out and just say, hey, class going on? And to give you attitude, I'll come out.
Give them an extra line.
The ruthenium
Thanks.
switched places.
Thanks, George. What's that?
Ruthenium switched places over here.
Oh, I did. Yeah, good catch. Good catch. Yes. No, yeah, good catch. So it's, yes, good catch.
Still works. Yeah, no, it still works.
Yes, good catch though, thank you. Okay, all right, so, so let's go through it if we went to the alkyne. So if you go to the alkyne, you can also get to this product. It turns out that I believe I have to go through it. I believe there's another alternative product that you can get.
You can do a ring opening with an alkyne.
Can you do ring opening with an alkyne? Go through the mechanism. I'm sure you could. I don't know what would happen. I'd have to think it through. But I would assume so. Like an E9 cross ring opening.
Usually have lots of screen.
You could probably, I have to think through the mechanism of that, but I'm sure something would happen, right? Because it would be a ring opening E9 metathesis. Yeah. Okay, so if instead you're up here, I'm just going to redraw it this time. Really, what's going to happen is I think depending upon which way you have the ruthenium, you can actually now get to two different products. So it turns out that from a productive standpoint, depending upon which way you start off with the ruthenium, and I'll go through this, but I'm pretty sure this is the case, that you can actually, unlike previously, where if you flip-flopped it, one you immediately recognize that one is not a productive pathway. With the alkyne, I think depending upon which way you draw it, you can actually get quite a ways down the mechanism path. Okay, so let's start with it this way. Okay, so if we are here, right, then we're going to do our 2 plus 2, retro 2 plus 2. I'm just going to flip that around. And we're going to have that. Am I right? 1, 2, 3, 4. 1, 2, 3, 4. Okay?
I get the same thing.
Right? And from this one, now we do the ring closing metathesis. And as Rami just sort of noticed, you're going to get to the same thing that we just got before. So if you did the metathesis reaction and you went this way, right, then chances are you were going to get the same product as if you did the alkene here. But let's just complete it just so that everybody can see. Right? And then we're going to do the retro 2 plus 2. Okay? And we're going to get there and we're going to leave the ruthenium alkylate. So this is one way that you could have gotten there from the alkene. However, it turns out that we go through this, just to double check. But I think if we flip-flop it, I think we're going to get to a different, I'm positive we're going to get to a different product. So let's go through that one. So we do the 2 plus 2 here. Now the ruthenium, instead of being here, is going to be out here. Right? Which means that when we do the retro 2 plus 2, this is not going to be our ruthenium. Ruthenium is going to be out here. You guys see that? I'm just sort of following through, right? So now where the diene was before, right? That's going to be this, and now our ruthenium alkylidine is going to be out there. Yeah.
Still do the ring. Still close the ring.
Yes, yeah, absolutely. But we're going to get to a different ring.
So like in a question like this.
Well, let's get back to in a question like this in a second. We're just doing practice. At this point, we're just practicing keeping, like, if you got this product, that's perfectly fine as well. Right now, we're just practicing going through the 2 plus 2, retro 2 plus 2 to see what we had. And so this was just simply a exercise in sort of trying an E9 metathesis, trying a metathesis on a slightly different structure. Right? So if we had to wrap this around, that's going to be a 1, 2, 3, 4, 5, 6, 7 numbered ring now. Right? Give me a second.
Get up to this point, it's not reversible.
So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 7 is going to have a double bond on it. 8 is going to have the ruthenium alkylidine on it. Right? Just do that. We do our 2 plus 2, retro 2 plus 2. Right? And we'll get to that 7-member ring. So, as we discussed, this is not ultimately the product that we're going to get, but I still think it's a decent exercise to go through the process and sort of see these differences. Right? So here's an instance where, in practice, we could envision getting a couple different molecules, and the question comes down, why is this so expensive to do? Well, maybe it's easier to do it with the alkene, right, first, because once we got the alkene, we were there. So. All right, so we've got about 10 minutes left. All right, so that's 10 minutes left. All right, so I think with that, I just want to make a couple announcements. And maybe we'll just let you go a little bit early. So next class is going. So Wednesday is going to be a review. The other thing about Wednesday is I'm probably going to try to leave rather early. So office hours, come in early. I may, depending upon what everything looks like, I may try to cancel a little bit to beat traffic out of the city because obviously Wednesday travel days are horrific. So if you have questions on office hours, try to get those answered quickly. What I would like to do is I would like to hold our Wednesday kind of like an office hour in many ways. So I'd like you guys to come with questions. If you want to, and so we can ask them here. If there's specific ones, you can email them to me so I can have them. I know Aisha, you already emailed me some that we didn't get a chance to get to today, but maybe we can get to some of those in office hours today or on Wednesday. But please email me if you have specific questions. And then as a reminder, exam number 2 is right after Thanksgiving break. So check this Monday. Yeah. No, it's Monday. So unless there's no school on Monday. Yeah. Huh? No. Do you know the heat that I would get if I did that? Because sure enough, one student would have rescheduled something around Monday. No, it's Monday. It's Monday. Yeah. My website does not work.
Yeah, it says down. The down is Saturday.
Is it bouncing in and out of being active?
Any hyperlink?
Okay, I'll take a look at it.
It's because of the BC website. It's not if you try using any hyperlink, it just says it's down.
So it's not on my website thing.
It
It's
is
a,
your website. No, it's not. It's not. This website is fine. School. Yeah.
so it's the school's issue. It's not mine.
Yeah, it's a school issue. The school's part.
I'll take a look. I'll take a look, but I can't promise. It sounds like maybe it's something out of my control.
I have a quick question.